Hello everyone. In this video, I'm going to give you a short overview about our work on optimizing round 2 candidates of the NIST lightweight standardization project on a RISC-V architecture. My name is Fabio Campos, and this is a joint work with Lars Jelemer, Mark Lemon, Lars Müller, Dan Sprenkels, and Benoit Villiers.
Before we start, I would like to talk about the main ideas of our project. As the main target of our work, we analyze different approaches for optimizing several candidates of NIST's lightweight cryptography standardization project on a RISC-V architecture. In particular, we study the general impact of optimizing symmetric key algorithms in assembly and in plain C. Let's start with some useful background. Let's briefly talk about our benchmarking environment. To write optimized code for a specific architecture, we need ways to measure improvements or regressions. Although in our work we use 3 different platforms for benchmarking, I will only present the results achieved on the Sci-Fi 551 board with an E31 core. The CPU implements the RV32 IMAC instruction set, which corresponds to the RV32I base instruction set with the extensions for multiplications, atomic and compressed instructions. The E31 runs at 320 MHz and uses a 5-stage single-issue in-order pipeline. Additionally, it uses a 16 kilobyte instruction cache. Optimized cryptographic implementations are usually written directly in assembly with the idea to prevent the compiler from introducing bugs or weakness and to achieve possible speedups. We call optimized C the translation of an assembly implementation back into C such that the code mimics the assembly instructions. By making sure we do not branch on secret data and considering the small size of the RISC-V instruction set, we trust the compiler to match our implementations. The underlying idea is to have the compiler further optimizing our code and taking care of the register allocation. Now, let's jump to the optimized algorithms, strategies, and the achieved results. Gimli is a NIST lightweight round 2 candidate which makes use of a sponge construction and is based on a 384-bit permutation. Its design puts emphasis on cross-platform performance and simplicity. The code is compact and uses only logical operations and shifts. The NIST submission includes a family Gimli cipher of authenticated ciphers and also includes a family Gimli hash of hash functions. As a baseline, the reference C code runs at 2178 cycles. By using careful scheduling of the instructions and using a minimum number of registers, our assembly implementations runs at 2092 cycles. By unrolling in C over 8 rounds and propagating the swapping by renaming variables to avoid move operations, the compiler manages to achieve further speedups by getting down to 1900 cycles, which leads to a 19% speed up for Gimli hash and Gimli cipher as shown in table 1. Sparkle is a family of cryptographic permutations based on the block cipher Sparks. Schwem, an authenticated encryption with associated data cipher scheme, and Ash, a hash function, follow a non-hermetic design approach and share Sparkle as their underlying permutation. Schwem and Ash work on a relatively small state, which is only 256 bits for the most lightweight instance of Schwem and 384 bits for the lightest variant of Ash. Unrolling the main loop within the Sparkle permutation over 7 or 11 rounds results in a significant speedup. We further optimize the permutation by avoiding the loading of the constants for the args boxes in every round, by loading and saving these 6 constants in the registers before the transformation. As shown in Table 2, our implementation achieves a speed up to 42%. Saturnin, a further NIST lightweight candidate, is built on top of a 256-bit block cipher with a 256-bit key. In their NIST submission, the authors described 3 constructions. One for hashing, called Saturnin hash, Saturnin short for authenticated encryption of small data, and further Saturnin cipher for larger data encryption. In the case of Saturnin, we optimize 2 32-bit available implementations. The BS32 and BS32X implementations both implement Saturnin in a bit-sliced fashion. Their difference is that BS32 bit slices inside of blocks, whereas BS32X bit slices across blocks. We tweaked the code to make sure that any constant would be loaded from SRAM and apply some greedily unrolling and inlining techniques. Table 3 presents the achieved results. Asken is a NIST lightweight round 2 candidate which uses a 320-bit large state. The authors of Asken introduce multiple variants of Asken for authenticated encryption as well as a hashing scheme. In this work, we focus our efforts on the Asken 128 authenticated encryption variant. We use the Asken C reference code as a baseline. More specifically, we use the reference, the 64-bit optimize and the 32-bit interleaved implementation as starting point for our optimizations. Our final implementation makes use of the improved S-box formula in a 6-round unrolled optimized C permutation. By folding the processing of associated data and message, we are able to reuse the code and have the compiled code fitting in the instruction cache. Applying these modifications, we achieved our best results, 15% faster than the baseline. Elephant describes a family of lightweight authenticated encryption schemes. One of the instances of Elephant is Elephant Keccak F200, also called Delirium, which uses Keccak as its permutation primitive. Delirium has a state size of 200 bits and claimed a security level of 127 bits. We optimize Delirium by exploiting Elephant's possibility for parallelization by using bit interleaving. In order to make full use of the 32-bit registers, we combine 4 blocks of byte-sized elements into 1 block of 4-byte elements. Thus, we can process 4 blocks at the same time and our state representation changed to an array of 25 32-bit words with a total size of 800 bits. As shown in Table 4, we note that short inputs perform worse in the optimized implementation. This is because the effort of interleaving data to process 4 blocks simultaneously is wasted if there are very few blocks to process. Zodiac, a further NIST lightweight candidate analyzed in our work, is a cryptographic scheme based on the pseudo permutation that's suitable for several symmetric key functions including hashing, encryption, MAC computation, and authenticated encryption. Pseudo iteratively applies 12 rounds to a 384-bit state, which can be treated as 3 horizontal planes, each one consisting of a 4 parallel 32-bit lane. The idea behind line complementing, first proposed in the Keccak implementation overview, is to reduce the number of not instructions by complementing certain lanes before the transformation. After additionally applying some loop unrolling, we achieve the speed up as shown in Table 5. Further, based on available RISC-V assembly implementations of AES, we improve the results of two variants. The first one is based on lookup tables, and the second one uses a bit-sliced approach. Although the key schedule is slightly slower, our approach gives us a 4% speed up in the case of the encryption in the CTR mode. Now, I'd like to compare our results with available implementations. We choose to compare our work against the repository of Weatherly, as their implementation are focused on good performance in plain C on 32-bit embedded microprocessors. As one can see in Table 6, the achieved speedups are in some cases over 50%. Now, let me present the conclusions of our work. First, with strategies such as loop unrolling, we are able to write assembly code close to the lower bound given by the number instructions arithmetic. Using the AES and Keccak assembly implementations, we also show that our approach is applicable to existing code bases. Although strategies such as fully unrolled loops may work nicely in simulated environments, they may fail on physical devices with instruction cache. Further, applying the bit manipulation extension in a simulated environment leads to a reduction of instruction up to 66%. Now, I would like to thank you very much for your attention. Check out our paper for further results, including some measurements on RISC-V simulators, also using the bit manipulation extension. Check out also our code, which contains all the implementations. Stay safe and goodbye.